No, 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 no. Number 4. Let's do the first one. What is the only value of x for which x squared minus 2019 squared over x minus 2019 equals 2020? Well, they want you to factor, so you can basically factor x squared at different squares. X squared minus 2019 squared is x plus 2019, x minus 2019, x over 2, x minus 2019 over x minus 2019. So that's just a giant 1. So you end up with x plus 2019 equals 2020, so x equals 1. But if you wanted to check it, or if you were like, just, I don't know, if you want to use your calculator, Inspire, you can do that, all right? Know how to use the solve feature. You solve, you plug it in, you also get the answer. It works both ways. Next question. 2 of the numbers I wrote on my paper are the greatest prime numbers. Remember, a prime number has exactly 2 factors, 1 and itself, less than 100 that differ by form. So you need the largest one. So you need to know what the primes are right around 100. Now, you could list them all. That could take some time. Here's a nice little trick. Take out your Inspire, and your calculator will prime factorize a number for you. So if a little trick to get all the prime numbers up to like 100%, let's say, is to factor 100 factorial, because 100 factorial is 100 times 99 times 98 times 97 and so forth and so on. So if you prime factorize 100 factorial, it will list out all the primes for you. Now notice you have to go up and you've got to scroll over to find the end. But over here at the end, you will see that the largest ones that are off by exactly 4 are 79 and 83. Those are the 2 you're looking for. 162. Answer. Next one. For what integer k will 2 to the k minus 1 be the greatest divisor of 2 to the 22nd minus 2? That is less than 2 to the 22nd minus 2. Well, notice you want it in the form 2k minus 1. We have it 2 to a power minus 2. There's lots of 2's in there. Let's just factor out a 2. Factor out a 2, and boom, you're pretty much done. You're looking for a divisor, all right? Or you're looking for a factor. So 2 to the 21st minus 1 is a factor of 2 to the 22nd minus 2. So k is simply 21. That was it. That was a nice, quick, easy one for number 3. Number 4. Total area of this parallelogram shown is 44. And the shaded area is 14. What is the region, the triangle that they have in common right here? So let's recall some geometry. Area of a parallelogram is base times height. Base times height, in this case, they tell us, is 44. That's the area of the parallelogram. And the area of one of these triangles that goes all the way to the top, not this little guy, but the one that goes all the way to the top, one of these triangles or the other one, they both have to have the same area because their area is 1/2 base times height. Here's your base. Your height is the perpendicular. It's the altitude is the perpendicular to the base. And so that's going to be exactly, because it's 1/2 base times height, same base, same height, it's got to be 22. So each of these triangles, the bigger triangles, are both 22. Now let's label some things. Let's call this little guy A and this one B. All right. Now we know that A plus B has to equal 22. Well, this triangle here would also have to be B, or have an area of B, because this A plus this triangle would also equal 22. So they have the same area. A plus B is 22 in both cases. All right. Now, it also turns out that B plus the shaded region must equal 22, because if A plus B is 22, so this triangle is 22, that means everything else is 22, and everything else would be the other B and the shaded area. So B plus shaded area equals 22. We're told the shaded area is 14. So if the shaded area is 14, then B plus 14 equals 22. That means B must equal 8. And if B equals 8 and A plus B is 22, then A has to equal 14. And here's another kind of cool thing. Since A plus B is 22 and B plus shaded is also 22, then that means A would have to always be the shaded region. No matter where these triangles lined up, you could move these top points all over the place, and that would change the area of the shaded region, but B would always equal 22. Cool. I mean, A would always equal 22. I mean, A would always equal 14. Let's go. What is the only value of x for which there are 24 positive integers, not necessarily distinct, whose sum is x and whose product is x? Remember, sum is when you add them all up. Product is when you multiply them. Now, we got to watch out because when you multiply things, if they get like that are positive integers, above 1, they get big really, really, really fast. But when you add things, they don't get big quite as fast. So let's first of all remember positive integers are like the counting numbers 1, 2, 3, 4, 5, and so forth. Not necessarily distinct means you can repeat numbers. So let's start small and get bigger. This is what I think of as like playful math. There's not like a formula that always solves this kind of problem. You just have to kind of play with the numbers and see what happens. It's also a little bit like guess and check, but you're not really doing just like random guessing and checking. So again, start small, get your bearings, figure out what's happening with this problem, and then start to work through the solution. So the smallest possible thing you could do is make them all 1. And let's just see what happens. If they're all 1, when you add them all up, you're going to get 24. And when you multiply them, you're just going to get 1. Now, this is kind of a nice place to start, especially because usually the product is going to be bigger than the sum. But in this case, we actually have the product is smaller than the sum. So now we can start to work our way up. All right, so picking all 1s doesn't work. So let's pick all 1s, but some other number. So there's going to be 23 1s and some other number, let's call it n. All right, we don't want to call it x because we're using x as the actual sum and product. So let's pick something else we're picking. So in this case, when you add them all up, there's 23 1s plus some number n. So the sum is going to be 23 plus n. And the product is going to be 1 times 1 times 1 times 1 times 1 times n. So the product is going to be n. Now 23 plus n only equals n. Never, because you're adding 23 to it. So this doesn't work. So we know that this doesn't work. So it's not 23 1s and n. So we have to move up to the next thing. So the next plausible thing to consider would be 22 1s and 2 other numbers. All right, let's pick one of those numbers to be 2, because again, products are going to multiply and get really big really fast. So we're going to pick one of the numbers is going to be 2, and then there's going to be another number n. We don't know what it is yet, so let's just leave it as n instead of like just throwing in random numbers. So the sum is going to be your 22 1s plus 2 plus n, and your product is going to be 1 times 1 times 1 times 1 times 1 times 2 times n, which is just 2n. Now we want these two things to be equal to each other. This is looking promising because we've got like just a nice linear equation here. So we set these things to equal to each other. So you get 24 plus n equals 2n, and just n equals 24. So if n is 24, then the product would be 48. The sum would also be 48. And we're technically done because it says there's only one value. Because you might be thinking, well, there might be other things that work for if I chose 3 in some other number or 4 in some other number. But they tell us that we don't have to look any further. You can actually, it's kind of a fun experiment and play around and see if you could find any others. Obviously, there aren't any out there. Wow, we already on to the last problem. Dang, that was fast. So point P is on the angle bisector of the base angle of an isosceles triangle whose base length is 12 and whose leg lengths are both 10. If the distance from P to the base is 2, what is the sum of the squares of the distances from P to the 3 vertices of triangle? Now, this is very wordy. There's a lot going on here, a lot of geometry involved. It's a number 6. It's supposed to be hard. But let's try and break it down and show that it's actually, if you've taken geometry, you've got the tools you need. You just need to figure out how to put them all together. So obviously, you got to start off drawing the triangle. There it is. Basically, an angle bisector splits an angle in half. So you're going to have an angle bisector like so, and then there's your point P somewhere on the angle bisector. Now, let's try to, when you first see a problem like this, think about your geometry and what you learned. All right, so let's think about isosceles triangles. Well, when it comes to an isosceles triangle, one thing that you should remember is that if you drop an altitude down, it will split it into 2 congruent right triangles. And because this is base is 12, each half is going to be 6, And now I can use Pythagorean theorem or my Pythagorean triples to realize that the height is just 8. So it's a 6, 8, 10, which is like a multiple of 3, 4, 5. So I know that the altitude's 8. Maybe that'll come in handy later on. I don't know, but it's like, think about what you know when it comes to isosceles triangles, because they made an isosceles triangle for a reason. So you typically are going to use some of these kinds of tools. Now, also, it's an angle bisector. So now you got to think back to, like, what did you learn about angle bisectors? Well, hopefully you learned that an angle bisector, the distance from a point on an angle bisector to one of the sides, what they mean by distance, they mean the shortest distance or the perpendicular distance. So if you draw this line straight down, it turns out that DF and DE are the exact same distance. You could prove this using side angle. But that's a good thing to know. It will come up later on. But there's also a more important thing, not more important, but as important, the angle bisector theorem. Anytime you have a triangle and you get an angle bisected in it, always think of angle bisector theorem, because you're going to use it like 99% of the time. So angle bisector theorem says that if you bisect an angle, then the ratio of the sides, of the two adjacent sides of the angle, will be the same ratio as the side that gets split and where it gets split. So A is to B as X is to Y. Sometimes you see it written as A is to X, as B is to Y. Same difference. Angle bisector theorem. So now we've got a bunch of tools that we can start playing with. All right, so let's go back to our original problem and let's see exactly what it's asking for again. So we're told that the distance from P to one of the sides is 2. So this is 2 right there. All right, I'm going to blow this up, make it a little bit bigger. And what we're asked for is the sum of the squares from P to the vertices. So we want what AP squared is, what BP squared is, and what CP squared is. All right. So let's try and figure out how to get there. Well, remember isosceles triangle. If I drop this down, CD would equal 8. All right. So I've got CD going all the way down here. Now, I've got a couple different triangles in here. Another thing to look for with these triangle problems is look for similar triangles, all right? Similar triangles happen a lot in triangle problems. So look for similar triangles, because then we can do all kinds of proportions. So do you see a similar triangle? Those guys right there, APF and AGD, those are similar triangles, all right? And I'm looking for AP, but because this APF is a right triangle, if I get AF, I can get AP. So can I get AF? Well, it turns out that I can't, because these are similar triangles. Let's see, let me get my bearings. Wait, I'm actually sorry. I'm going to do that in a second. I can't do it yet. And here's why. AF to 6 is going to be 2 to GD, but I don't have GD yet. All right, so I need to solve for GD first. So to solve for GD, what I'm going to need to do is angle bisector theorem. So I can find GD by calling, if this whole thing is 8, I'm going to call GD X, and then I'm going to call CG 8 minus X. So if this is X, this is 8 minus X. All right, again, angle bisector theorem. I'm not using the second half of the triangle. I'm using just the triangle ACD, using the angle bisector theorem for that. And now I can set up my ratio as 6 is to 10 as X is to 8 minus X. So 6 is to 10 as X is to 8 minus X. So X ends up equaling 3. All right, so GD is 3. Now I can go back and do my similar triangles, and I can say that Y is to 2 as 6 is to 3. And if Y is to 2 as 6 is to 3, Y is simply 4. So now we're getting somewhere. So Y is 4, all right? So now we can figure out what AP is, because we have two sides of a right triangle. So you just square this, square that. Now we don't actually have to solve for AP, because we want AP squared. So we can just, once we square 4 and square 2, that's what C squared is, or AP squared is, we can stop. All right, now we got one piece of it. Now we need to find the other two pieces, but we are almost home here, because remember, this point for P, since it's on the angle bisector, P to F is going to be the same as P to whatever, wherever it hits AC. That's also going to be 2. These are both congruent triangles, so this is going to be 4. Right? Now, if this is 4 and this whole thing is 10, then this is 6 over here. So if this is 6 and this is 2, I have another right triangle. And if this is 4 and this whole thing was 12, then this is 8. So this is 2. And now I'm pretty much done because I can figure out what BP is, because that's just going to be 8 squared plus 2 squared. I can figure out what CP is, because that's going to be 6 squared plus 2 squared. And then I take these three, add them all up, 128. That's how you get a 6, people. All right. Nice job. Have fun. Bye.